Okay, yeah, okay. Hi, everyone. Welcome back, ladies and gentlemen. I see some guys still playing like Team Fortress 2. Please stop that. So we're back. So what's up this week? Homework 1 is now posted. Okay, so that's available on the course blog. Before you go and pull that up, I ask that you please just fill out this short survey. So if you go to the survey here, please take a couple minutes and fill that out. And then we'll talk a little bit about what's expected on the homework. Okay, so take a moment, pull out your device, go to the course webpage here, and fill out the survey. Okay, and also people who are doing the web option, please do the homework too. Okay, so very good. 5 minutes after the beginning of tutorial. So you have to hand them in your tutorial next week. Sorry, yeah. So if you hand in your homework after 1:15, I've instructed the TAs to just give you 0 on the spot, no chance for appeal. Okay, so it'll just be 0, and that's one assignment the TA doesn't have to mark. So they're happy to do it. Okay. If you think that you might be late for tutorial because maybe you come in from another city or something, email it. Okay. In order to facilitate that, please try and write very, very, very clearly. Okay, so write your solutions on lined paper. If you are interested, I encourage you to try and learn how to type up math on a computer. So to learn the software that I used to make this, this handout. Okay, so that's called LaTeX. It looks like it should be pronounced latex. It's pronounced LaTeX. Okay, so what's on the homework? There's a couple things about prerequisites. We didn't cover this material in class. It was covered in courses before this one, but we want to see if you still remember it. And then there's a couple questions from the new material. Okay, there's also a bonus question here at the end, which is kind of like a short essay thing. Okay, so find an application of the dot product in your actual studies or in actual computer science. Okay, and then there's a couple of these questions that have already been assigned. So if you're one of the people who did the homework, you've probably already completed question 29 and 15. Okay, so that's kind of going to be the layout of all of the assignments. Please type it up as best you can and hand it in before the, yes. Yes, yeah, yeah. That's why it's called a bonus. And it's not, it's kind of like an all or nothing, it's just to get you thinking about how this stuff would actually be used in your careers or in your lives. Okay, yeah, questions, yeah? Yeah, totally. Yeah, you can get more than 100. Yeah, definitely. Any other questions or thoughts? Questions or thoughts about the homework? Yeah, sure. Oh, that's a good question. I don't know. I'll think about that. Yeah. Yeah, I'll send an announcement to the class. Yeah, good point. One more thing about tutorials. The information about tutorials and stuff is now here. So the TAs have been assigned. Okay? I just want to remind everyone, TAs are people too. Okay? They have names. They have parents. So please get to know your TA's name. So here's your TA's name. Here's their email address. So if you want to submit your homework electronically, the email addresses are there. Okay, so that's under course staff. And then there are the tutorials. And that answers your question. There are no tutorials on Monday. It seems. Okay, any other questions or thoughts? Ideas? Okay, so let's get on with it then. Very good. Shut down this thing. Okay. Okay, so Okay, so what's the plan for the week? What do we want to get done this week? Okay, we're going to talk about matrices. That's going to be the topic of tonight's lecture. Then we'll get into the topic of determinants. And the cross product. Okay, so right now, today we're just going to say a little bit about matrices. Okay, so for a lot of people this will be review, but I want to emphasize a couple perspectives on matrix multiplication that you might not have seen before. Okay, so these are sort of potentially new perspectives on matrix multiplication. Okay, so recall from last week, right? We had this notion of a dot product. Okay. Okay, so what do I do to get the value of a dot product? Yeah, any thoughts? Yeah, sure, here.
Isn't it also defined as A times B transpose?
We're not quite there yet. Yeah, we didn't define it that way last week. How did we define it last week? Yeah. So I take this product, right? I take U1, V1, U2, V2, U3, V3. Okay, so I take the corresponding entries, multiply, and then add up to get my final result. Oh, whoops. Yeah, I'll leave that there. Okay. Okay, we're going to define matrix multiplication. Using a notion of dot product. Okay, so we're going to define matrix multiplication so that it works like this. Okay, so our basic example of how to multiply things is going to be columns and rows, and this will wind up being the following product, which is again the dot product that we know and love. Okay, so it's we define matrix multiplication so that for a row and a column, we know how to line things up and what happens. Okay. Oh, that's in the way. Oh, thank you. You're a hero. Yeah, very good. Yeah, just smush it all in. That's fine. Okay. Cool. Thank you. Okay, so we're going to define matrix multiplication so that this happens. So so our matrix M, which has entries ij, we define blue chalk. Okay, so the transpose you've probably seen in a previous course. We write with a T here, and that's the matrix with these entries reversed. Okay, so I and J flip places. So a simple example of a transpose would be something like this. Okay, we switch the rows and columns of our matrix. Okay, so this first row becomes the first column. This second row becomes the second column. Okay, very good. So that's a transpose. And now we get to this point that was made about dot products. So okay, if we've got two vectors, then if we're writing everything as columns, we can think of the dot product as U transpose times V, okay, using our notion of matrix multiplication. Okay, any questions or thoughts about that idea? So this is just rephrasing the dot product in terms of transposes and matrix multiplication. Okay, so very good. So now we can define what we mean by matrix multiplication for matrices in general. Okay, so if we've got an n by k matrix and a k by l matrix that we've set up like this, okay, so what do I mean by these horizontal lines? I mean that these are rows, and by these vertical lines, I mean that these are columns. Okay, so these are row vectors. These are column vectors. Okay, then we can define a product that looks like this. Okay, so we define our multiplication of these two matrices as a bunch of dot products. Right? So we take row I from this guy, and we dot product it with column J from this guy. Okay? So this is another way of interpreting what's going on when we do matrix multiplication. So let's see an example of how that looks. Okay, so here we want to split this guy into rows. And we want to split this guy into columns. Okay, so setting things up with the notation that we used over here, 1, 2 becomes our first row, 3, 4 becomes our second row. Okay, and now our matrix multiplication looks like this. Good. Okay, and now when we multiply them, we fill out the following thing. Okay, so this is just an alternative interpretation of the usual matrix multiplication. So we get the usual answer, which is 1, -1, 3, -1, I think. Yeah. Okay, so this will be useful for sort of theoretical reasons later on. But I just wanted to set things up in terms of dot products to see how we can get matrix multiplication to work using dot products. Okay, there's one other sort of new interpretation of matrix multiplication that I want to share with you. Okay, so one way of thinking about the product matrix times vector is as follows. Okay, when we do this calculation, when we multiply this guy against these columns, we get the following thing. So we get 5, 12, so that's 17. Okay, so this is just using our usual convention of matrix multiplication, but we can also think of this in the following way. Okay, so these numbers here, 5 and 6, act as the guys that stretch our vectors. So we take the columns of our matrix and we stretch them by the entries here. Okay, this is occasionally useful for doing calculations. Okay, so take a moment. Okay, so take a moment and try and formulate this product using the dot product. Okay, so apply the ideas over here to this idea of putting the coefficients out front. Okay. So take a moment, discuss it with your neighbor, discuss what's on the board, and see where you can get with it. Right, so while we were discussing, someone pointed out a good typo. So there's a little bit of a note. When I say that a matrix is n by k, I want it to have n rows and k columns. Okay, so for this to be correct, we need that this goes from 1 to n, and then this goes to L. Sorry, yeah, so this actually should go to L. Okay, here we've got n rows, and here we've got L columns. Okay, so there's a little bit of a typo there that's worth mentioning so that the product works out the right way. Okay, Very good. So let's try and formulate this matrix product, matrix vector product with the dot product. Okay, so we always think of matrix multiplication with this guy as a row and this guy as a column. So this will look like this. Okay, and if this is a vector, then it consists of a single column. Okay, so what we get when we compute the product is the following thing. Okay, so this is why we wind up with the entries of that column mattering so much. The entries of this column get multiplied by our guys here, right? So this winds up C1 gets multiplied on each of our rows. Okay, very good. So I wanted to just kind of put a bit of emphasis on that point with the matrix vector product. Okay, so we've got a couple more things to do regarding matrices. Okay. Yes, sure. Yeah. Yeah, everything gets dot product C1. So these are all dot products. Does that clear things up? Okay, cool. Okay, so matrix inverses are things with the following property. Okay, the inverse of a matrix M is M inverse, so that the following happens. Okay, so that these guys multiply out to give the identity matrix, and the identity matrix is the guy with 1s along the diagonal and 0 everywhere else. Okay, so I write I for the matrix with this form. Okay, very good. So that's what an inverse does. I want to lay out a particular algorithm for finding matrix inverses. Okay, so from time to time we're going to have to invert some matrices. How do we go about doing that? Okay, our goal is to invert the matrix M. Okay, so our first step is to set up this, this augmented matrix. So we put M here, and we put the identity here. Okay, so we're going to row reduce this guy to something A M twiddle. Okay, so we row reduce it as far as possible, and we get the following statement. If A is equal to I, then M twiddle is our matrix inverse. Otherwise, okay, if that doesn't happen, then our matrix is not invertible. Okay, so we row reduce until we get to A M twiddle. If we can row reduce until we have the identity, then we're good. We have an inverse. Otherwise, the thing's not invertible. Okay, so this is a very practical algorithm, assuming you can row reduce. Okay, so very good. So let's see that in one particular case. Okay, so let's try this out. Okay, so what do we do? Okay, we start off here with our augmented matrix. Yes, sure, yeah. Oh yeah, weird. Right, yeah, sorry. Yeah, very good. Good typo catch. It's the worst when I do the example all the way and then someone says, wait, wasn't the first step wrong? It's the worst. Okay, so we start off here. We want to row reduce this thing as far as possible. So we're going to do 1/2 of R2. Okay. Now we have a leading 1 here, so we're going to subtract that off. Okay, now we've got to a place where we have the identity matrix on this side. So thus, an inverse is this. Okay. One thing I want to advocate for a lot in this course is techniques for checking your work. Once you've done a calculation, how do you know that you did it correctly? Right? So in order to check our work, okay, so how do we go about checking a matrix inverse? What would be a good test? Yep. Yeah, multiply the two things out and see what we get. right? So as usual, we work row versus column. Okay, so it multiplies out to be the identity. So we did it right. We found the right inverse. Okay, so these techniques are just helpful for checking your work once you've done it. Are there any questions or thoughts so far? Okay, so before coming to lecture today, I was trying out the recommended exercises, and I found one that's really hard. So I want to go through it kind of as like a prequel to next lecture. Okay. Okay, so yeah, so you guys are so chatty tonight. I feel like I've got like my grade 6 students again. So I volunteer at a public school sometimes and they're just like, they're everywhere. Anyway, very good. So this is the question that I thought was quite hard. So this is from the homework. Which question was it? I didn't write down the question number. So the reason that this is hard is it's hard to approach with the tools that we have right now. Right? We don't know what it means to lie on a unique plane, really. So we want to find some condition that means things won't lie on a unique plane. Okay? So if we imagine just sort of 3 generic points in space, right? If we just imagine sort of these as being 3 points in space, we could imagine a plane sitting on top of them kind of firmly like this, right? So one way in which they could fail to lie on a unique plane is if all 3 points lie on a line, right? Then we would have many, many planes that contain those points. Okay, so the observation is, and this is like the clever observation, okay, if they lie on a line, then we get no unique plane, right? If they were not on a line, then we would get a unique plane. Okay? So what we have to do is we have to find the line that contains them. Okay. Okay, so let's consider a line made out of the parts that we have. Okay, so we start off here, right? We start off with this as our base point. And then we go from this guy to this guy. Okay, so we've used up all 3 points. And we get the following. Okay, but it's not clear what to do with this line now. Okay, so when we plug in t equals 0, we get this, which is our first point, right? So we've got this point here. Okay. Then when we plug in t equals 1, we get one, 4, 0, which is good. So that's our second point. Okay, and now what do we have to plug in to get the third point on this thing? What value will give us the third point? Okay, I'm seeing a show of hands. Any guesses? Okay, I'm seeing a bunch of 2s, and that's correct, yeah? But we really have to stare at these points to see that value 2. Okay, so thus, okay, so thus all 3 points lie on a line, and any plane containing that line will contain these 3 points. Okay, any plane containing this line will contain our 3 points. Okay, and then there's infinitely many planes that'll contain these guys. Okay, so I wanted to demonstrate this solution to get us ready for what we're going to do on Thursday. Okay, so on Thursday, we're going to move into determinants and cross products. And then we'll find a much nicer way to do this question. Okay.